March 1973, the launch occurred in absolute secrecy during the early morning hours of March 6, 1973, from Vandenberg Air Force Base, California. The Atlas-Agena D rocket tore through the atmosphere carrying an object that officially did not exist. No press release, no public broadcast. Only a single encrypted line transmitted to Fort Meade, Maryland, headquarters of the National Security Agency, confirming that the payload had reached geosynchronous orbit above the Horn of Africa at 35,786 kilometers altitude. The technical designation was known only to a restricted circle of analysts within the CIA, NRO, and NSA. RHYOLITE was operational. For years, Soviet communications officers had operated under the conviction that their terrestrial microwave transmissions were immune to Western interception. The logic was simple and technically irrefutable. Microwaves travel in straight lines. They do not follow the Earth's curvature. They do not bounce off the ionosphere like lower-frequency radio waves. To intercept a microwave beam transmitted between two ground towers separated by hundreds of kilometers deep inside the Soviet Union would require positioning receivers within Soviet territory, infiltrating agents with sophisticated technical equipment, or violating airspace with specialized aircraft. The Soviets knew the Americans did all of these things. But they also knew these operations were risky, geographically limited, and vulnerable to counterintelligence. What Moscow had not anticipated was that the United States could position a 21-meter diameter parabolic antenna directly above their most sensitive communications centers, permanently, without risk of shoot-down, without need for exfiltration, and with continuous monitoring capacity for years. When RHYOLITE began intercepting military command communications, encrypted diplomatic transmissions, and most critically real-time telemetry from intercontinental ballistic missile tests launched from the Tyuratam and Plesetsk complexes, Soviet communications security planners realized they had committed a strategic error of catastrophic proportions. Soviet arrogance did not reside merely in underestimating American space engineering. It was rooted in confidence that the basic physics of microwave propagation provided inherent security. Point-to-point transmissions between ground stations separated by tens or hundreds of kilometers, operating at frequencies between 2 and 18 gigahertz, simply could not be intercepted from outside national territory. The geometry was prohibitive, but the Americans had weaponized that same geometry. By positioning satellites in geosynchronous orbit, remaining fixed relative to specific points on Earth's surface, they could capture not only the direct transmissions between towers, but also the inevitable lateral dispersion of microwave beams that escaped vertically toward space. The program had been born in 1963 during a strategic review conducted by the CIA under the codename Rainfall. Intelligence analysts faced a seemingly insoluble technical problem. The Soviet Union was expanding its long-distance communications network using high-capacity microwave links. These networks carried military command traffic, Politburo communications, coordination between weapons research centers, and most importantly for NRO analysts, detailed telemetry from strategic missile tests. Aircraft like the U-2 could intercept some of these transmissions during border overflights, but coverage was sporadic and dangerous. The shoot-down of Francis Gary Powers in 1960 had proven that Soviet airspace was not territory for routine intelligence collection. The solution proposed by CIA engineers was radical. Instead of attempting to penetrate Soviet territory horizontally, they would do so vertically from above permanently. Signals intelligence satellites in low orbit already existed. The designated Canyon had operated since 1968, intercepting VHF radio transmissions. But Canyon orbited at only 850 kilometers altitude, crossing Soviet territory in passes of minutes, incapable of maintaining continuous surveillance over specific targets. RHYOLITE would be different: geosynchronous orbit, fixed position, uninterrupted monitoring of critical geographic zones, and an unprecedented deployable parabolic antenna to capture weak signals from over 35,000 kilometers away. The National Reconnaissance Office awarded the contract to TRW Systems Group in 1965. TRW's M4 building in Redondo Beach, California, a windowless facility with maximum security, became the development center. Their engineers worked in isolated shifts building a system that, when packaged for launch, was approximately half the size of a railway car. Once released in orbit, the satellite unfolded like an accordion. Solar panels extended, three-axis stabilization systems engaged. And the parabolic antenna, composed of high-precision metal mesh segments attached to an expandable radial structure, gradually opened until reaching 21 meters in diameter. creating a concave surface capable of capturing diffuse microwaves at frequencies between 100 MHz and 18 GHz. The first prototype, RHYOLITE-1, was launched on June 19, 1970, and initially positioned at 105 degrees east, directly above the Indian Ocean, enabling simultaneous coverage of the Baikonur and Sary-Shagan launch complexes in Soviet Kazakhstan. The intercepted signals were not relayed directly to the United States. Instead, they were transmitted to a ground station located in central Australia, 18 kilometers southwest of Alice Springs, Pine Gap. The facility, officially designated Joint Defence Facility Pine Gap, was jointly operated by the Australian Signals Directorate, CIA, NSA, and NRO. Pine Gap housed 38 radomes, white geodesic structures protecting parabolic antennas that continuously tracked RHYOLITE satellites in orbit. Australia's geographic location was critical. It provided direct line of sight to satellites positioned over the Indian Ocean and Southeast Asia, enabling continuous data reception without interruption. RHYOLITE-1 operated for at least 5 years. During the Indo-Pakistani War of 1971, the satellite was repositioned to monitor military communications on the subcontinent. During the intensification of the Vietnam War, it was moved again to intercept North Vietnamese and Chinese transmissions, but its primary target remained constant: Soviet missile telemetry. Each ICBM test conducted at Tyuratam or Plesetsk transmitted thousands of data channels in real time. Information on engine performance, guidance system accuracy, stage separation sequences, warhead reentry characteristics. These transmissions were intended for Soviet ground tracking stations along the flight trajectory. But a significant fraction of the radiated energy escaped vertically, dispersing into the upper atmosphere where RHYOLITE waited. The intercepted data was relayed via Pine Gap to Fort Meade within minutes. NSA analysts decoded the telemetry, extracting detailed technical specifications: range, velocity, accuracy, payload capacity, system reliability. The Soviets were involuntarily providing the United States with complete technical reports of every strategic weapon test, and they did so repeatedly, believing their transmissions were confined to national territory. Soviet Technical Arrogance and Communications Security Doctrine. Soviet Communications Security Doctrine of the 1960s and early 1970s was built upon technical principles that in isolation were sound. Microwaves, due to their short wavelength between 1 mm and 1 meter, propagate in straight lines and do not follow Earth's curvature like low-frequency radio waves. Consequently, point-to-point microwave links between towers separated by long distances were considered secure against remote interception. As long as the transmitting and receiving antennas were precisely aligned and the beams were narrow and directional, the possibility of capture by third parties was theoretically limited to those physically positioned in the direct line of transmission or in immediate proximity. This confidence was reinforced by massive investments in microwave infrastructure during the 1950s and 1960s. The Soviet Union developed an extensive network of relay towers spread across its vast territory, connecting urban centers, military installations, industrial complexes, and strategic command bases. The system carried not only civilian telephony and data communications, but also classified military traffic, including command orders, intelligence reports, and logistical coordination. More importantly, the ballistic missile test centers at Tyuratam, Plesetsk, and Kapustin Yar used microwaves to transmit flight test telemetry to ground tracking stations distributed along missile trajectory routes. What Soviet planners had not adequately considered was the physics of beam dispersion. Although microwave beams are highly directional, no antenna produces a perfectly collimated beam. There is always a small fraction of energy that escapes laterally and vertically, forming secondary radiation lobes. These secondary lobes are weak compared to the main beam, but they are not non-existent. Under normal conditions, this dispersion is irrelevant. The energy escaping vertically dissipates into the atmosphere and space without practical consequence. But if a sufficiently sensitive receiver, equipped with a sufficiently large parabolic antenna, could be positioned directly above the transmission route at an altitude where signal density was still detectable, interception became possible. The Soviets were aware of American capability to launch satellites into geosynchronous orbit. They knew the United States operated photographic reconnaissance satellites like Corona and later Hexagon. They knew that early warning satellites like DSB were positioned in high orbits to detect missile launches via infrared sensors. but the idea that a satellite could be equipped with a parabolic antenna of sufficient size to capture weak microwaves radiated from ground towers over 35,000 kilometers away seemed, at best, technically improbable. This underestimation was compounded by an intelligence failure. During RHYOLITE's initial development between 1965 and 1970, the KGB had not detected the program. The project was compartmented within the CIA and NRO under highly restricted access codes. TRW Systems Group, responsible for construction, operated under rigorous counterintelligence measures. Launches were conducted under generic codenames without public disclosure of objectives or capabilities. Pine Gap, the crucial ground station in Australia, was presented externally as a joint Australia-United States space research facility. Mid-level Australian officials working in unclassified sectors of Pine Gap had no knowledge of the operations conducted in the restricted cryptological rooms where American analysts processed Soviet telemetry in real time. The first sign that something was wrong emerged in 1973, shortly after RHYOLITE 2 became operational. Soviet counterintelligence analysts began noticing inexplicable discrepancies. Arms control negotiations, particularly the SALT strategic arms limitation talks, conversations, revealed that the Americans possessed detailed technical knowledge of Soviet missile systems that should not be accessible via photographic reconnaissance or human intelligence collection. Engine performance specifications, failure rates, incremental modifications between missile generations. This level of knowledge suggested direct access to telemetry data. Internal investigations began quietly. Security auditors reviewed transmission protocols. Microwave networks were examined for possible terrestrial vulnerability points. Suspicions initially fell on human penetration, infiltration of agents within test centers, or corruption of personnel with access to technical data, but no conclusive evidence was found. The possibility of space-based interception was briefly considered and largely dismissed as implausible due to presumed technical limitations. This posture changed dramatically in January 1977 when two young Americans were arrested for espionage. Christopher John Boyce, 23, and Andrew Dalton Lee, 25, had sold classified documents to the Soviet Union between 1974 and 1977. Boyce worked at TRW Systems Group in Redondo Beach, California, at the heart of the RHYOLITE project. His position in the Black Vault, TRW Classified Communications Center, granted him access to encrypted transmissions from the NRO and CIA related to intelligence satellite operations. Lee, a drug dealer and Boyce's childhood friend, acted as courier, transporting photographed documents to Soviet officials in Mexico City in exchange for money. The documents Boyce delivered to the Soviets included RHYOLITE technical specifications, information about Pine Gap, details on CIA encrypted communication systems, and crucially, confirmation that the United States was intercepting Soviet missile telemetry directly from space. When Lee was arrested by Mexican police on January 6, 1977, he was carrying photographs of documents classified top secret relating to a TRW study for the CIA on a global satellite communications system intended for agents in denied areas of the world. Lee confessed his espionage role and implicated Boyce. During subsequent interrogations and the public trial, details of the RHYOLITE program began leaking to the media. The revelation caused silent panic in Moscow. The Soviet Union realized it had operated for years under the false premise that its most sensitive strategic communications were secure. Thousands of hours of missile telemetry, military transmissions, diplomatic communications, and weapons research coordination had been captured by American satellites without interruption. The scale of the vulnerability was monumental. This was not a point breach by an infiltrated agent or an occasional spy aircraft overflight. It was continuous, systematic, broad-spectrum surveillance over areas Moscow considered impenetrable to Western intelligence. RHYOLITE Technology and Operations RHYOLITE, and its subsequent designation Aquacade after 1977 when the original name became public, represented a convergence of multiple technological innovations. The central challenge was building a satellite capable of capturing low-power signals at unprecedented distances, processing those signals onboard to distinguish useful telemetry from ambient noise, and relaying the captured data to ground stations without significant degradation. The antenna was the most critical component. At 21 meters diameter in the initial configuration, RHYOLITE's parabolic antenna was, at the time, the largest deployable structure ever deployed in orbit. The reflective surface was not solid but composed of high-precision metal mesh tensioned over an expandable radial structure. This design reduced the satellite's total mass, enabling launch via Atlas-Agena D rockets, while maintaining the optical properties necessary to focus microwaves onto receivers mounted at the parabola's focus. The mesh was adjusted with millimeter tolerances to ensure reflected signals converged correctly, maximizing system sensitivity. The deployment mechanism was an engineering marvel. After separation from the propulsion rocket and insertion into geosynchronous orbit, automated commands initiated the expansion sequence. Articulated structural panels opened radially, locking into position via pin and spring systems. The antenna mesh, stored compactly during launch, was gradually tensioned by perimeter cables until reaching the desired parabolic curvature. Onboard sensors monitored the antenna's geometry, adjusting tension as needed to compensate for thermal distortions caused by alternating exposure to sunlight and Earth's shadow. The receivers operated across multiple frequency bands. The primary range of interest for intercepting Soviet missile telemetry was between 200 MHz and 10 GHz, covering frequencies used by transmitters installed on Soviet ICBMs like the R-7, R-16, R-36, and later generations SS-16, SS-17, SS-18, SS-19, and SS-20. Each missile transmitted telemetry on multiple channels simultaneously, enabling redundant monitoring of critical systems during flight. Accelerometers, gyroscopes, fuel pressure sensors, engine temperature sensors, stage separation systems, each transmitted data continuously from ignition until warhead impact at test ranges in Kamchatka or the Kazakhstan desert. RHYOLITE did not record these signals in raw form. The satellite was equipped with onboard analog processors that performed initial filtering, separating telemetry signals from background noise, atmospheric interference, and unrelated transmissions. This signal discrimination capability was essential. The density of the electromagnetic spectrum over Soviet territory was high. Civilian radio broadcasts, aviation radars, lower priority military communications all generated noise that could saturate receivers if not properly filtered. The onboard processors used known characteristics of missile telemetry, such as frequency modulation, data transmission rates, and frame structures, to isolate relevant signals before relay. Relay to Pine Gap operated in X-band between 7 and 8 GHz, using a high-power directional transmitter continuously aimed at the Australian ground station. The choice of geosynchronous orbit was crucial here. Because the satellite remained fixed relative to a specific point on Earth's surface, Pine Gap's antennas did not need to continuously track a moving target. They could be adjusted once and maintain uninterrupted communication 24 hours a day, 7 days a week, except during solar eclipses when the satellite passed through Earth's shadow and temporarily relied on onboard batteries. Pine Gap was not merely a reception station. It was a real-time intelligence analysis complex. The 38 radomes housed not only communication antennas, but also large-scale computing systems that processed raw data received from RHYOLITE satellites in orbit. Analysts from the NSA, CIA, and Australian Signals Directorate worked in continuous shifts, decoding telemetry, correlating transmissions with known events like missile launches detected by DSB early warning satellites, and producing intelligence reports that were transmitted via encrypted lines to Fort Meade and Langley within minutes of interception. Pine Gap's capability was amplified by a critical factor: absolute secrecy. The facility was publicly presented as a scientific space tracking station. Low-level Australian personnel worked in administrative and maintenance sectors without access to intelligence operations. Only personnel with top-secret clearance and specific compartmented access could enter the cryptological rooms where Soviet telemetry was processed. This compartmentation was so rigorous that during the Yom Kippur nuclear crisis in 1973, when Secretary of State Henry Kissinger issued a global DEFCON 3 alert, Pine Gap was placed on nuclear alert without the Australian government or Prime Minister Gough Whitlam being informed. The station was, for all practical purposes, American operational territory embedded in Central Australia. The data collected by RHYOLITE was of incalculable strategic value. During development of the Soviet R-36M intercontinental ballistic missile, known to NATO as SS-18 Satan, RHYOLITE captured complete telemetry from multiple flight tests conducted between 1973 and 1975. This telemetry revealed that the SS-18 was a two-stage liquid fuel missile with a range exceeding 11,000 kilometers, capable of carrying 10 MIRV, multiple independently targetable reentry vehicle, warheads with sufficient accuracy to threaten American Minuteman missile silos in a first strike. The telemetry also revealed failure rates, guidance system vulnerabilities, and deployment timelines. This information was used directly by American negotiators during SALT II talks, enabling the United States to press for specific limits on heavy missiles based on precise technical knowledge of Soviet capabilities. Another critical application was monitoring diplomatic and military communications. Although RHYOLITE's primary mission was TELINT telemetry intelligence, the system also captured COMET communications intelligence, microwave links between Moscow and remote military bases, between the Kremlin and Soviet embassies in distant regions, between naval command centers and fleets operating in the Indian Ocean. All these channels were vulnerable. When communications were encrypted, NSA analysts could not necessarily decode them in real time. But they could record the encrypted traffic, analyze communication patterns, identify increases in activity suggesting military preparations or political crises, and in some cases exploit flaws in Soviet cipher implementations. In 1975, an advanced RHYOLITE prototype was launched under the codename Argus. This satellite, reported to have an approximately 43-meter diameter antenna, nearly twice the size of previous generations, represented a significant leap in interception capability. A larger antenna captured weaker signals, enabling monitoring of lower power transmissions, interception of tactical military communications previously below detection threshold, and coverage of additional frequencies. Argus was positioned over Southeast Asia, providing coverage of China, North Vietnam, and Soviet targets in eastern Siberia. Between 1970 and 1978, 4 operational RHYOLITE satellites were launched. RHYOLITE 1 June 1970, RHYOLITE 2 March 1973, RHYOLITE 3 December 1977, and RHYOLITE 4 April 1978. Each satellite's operational lifespan varied between 5 and 7 years, depending on electronic component degradation, attitude control propellant depletion, and mechanical deterioration of the deployable antenna. A constellation of at least 2 satellites was continuously maintained in orbit to guarantee redundant and uninterrupted coverage of priority geographic zones. The program designation was changed from RHYOLITE to Aquacade after the public revelation caused by the Boisley case in 1977. But the name change did not represent alteration of mission or technical capabilities. It was simply a standard operational security measure, reclassifying the program under a new codename to hinder tracking by adversary intelligence services. Subsequent generations of geosynchronous SIGINT satellites were developed with expanded capabilities under new codenames, including Magnum in the 1980s and Orion from 1995. But the fundamental architecture established by RHYOLITE, giant parabolic antennas in geosynchronous orbit relaying intercepted signals to Pine Gap, remained essentially unchanged. Soviet reaction and doctrinal collapse confirmation that RHYOLITE had been operational since 1970, capturing missile telemetry and strategic communications for 7 years before discovery, represented a devastating blow to Soviet national security. The impact was not merely technical but psychological and doctrinal. Soviet leadership realized they had operated under an illusion of security, transmitting information they believed was protected by the basic physics of microwave propagation, while every byte of data was being recorded and analyzed in real time by American analysts thousands of kilometers away. Internal KGB documents from after 1977, partially revealed following the Soviet Union's collapse, indicate that RHYOLITE's discovery triggered a massive security audit. All strategic communications networks were reassessed, transmission protocols were revised, significant investments were directed toward developing buried fiber optic links and underground coaxial cable communications as alternatives to terrestrial microwaves. But these solutions required time, massive financial resources, and infrastructure reconstruction on a continental scale. The immediate solution was more robust encryption, but encryption does not conceal metadata. Even if transmission content was enciphered with unbreakable algorithms, the Americans could still analyze traffic volume, communication patterns, transmission origin and destination, and activity timing. During preparations for missile tests, for example, increased communications between the Ministry of Defense in Moscow, strategic missile command centers, and launch bases was detectable. This allowed the United States to position additional intelligence resources, including photographic reconnaissance satellites and electronic interception aircraft, to monitor tests in advance. Another adopted measure was attempting to reduce vertical dispersion of microwave beams. Soviet engineers developed antennas with more suppressed secondary lobes, concentrating radiated energy more tightly in the main beam between transmitter and receiver. But this approach had physical limits. Complete suppression of secondary lobes was impossible without sacrificing overall communication system efficiency. Moreover, RHYOLITE and its successors were becoming progressively more sensitive. Later satellite generations with larger antennas and more sophisticated receivers could capture increasingly weak signals. It was an asymmetric technological race. The Soviets attempted to minimize energy escaping vertically. The Americans increased detection sensitivity. And the Americans had the strategic advantage of geosynchronous orbit, a position geographically invulnerable to direct countermeasures. The KGB also intensified counterintelligence efforts specifically targeted at Pine Gap. Soviet agents attempted to infiltrate personnel into the facility or recruit Australian employees with access. Public protests against Pine Gap were discreetly encouraged, aiming to create political pressure on the Australian government to close or restrict American operations. These efforts had limited success. Pine Gap continued operating without significant interruption, and the Australian government, though occasionally politically embarrassed, maintained its commitment to the intelligence alliance with the United States. Perhaps the most significant impact was on arms control negotiations. During SALT II, Soviet negotiators realized the Americans possessed detailed technical information on Soviet weapons systems that could only originate from intercepted telemetry. This placed the Soviet Union at a negotiating disadvantage. The United States could propose specific limits based on precise knowledge of Soviet capabilities, while Moscow lacked equivalent access to American missile test telemetry. Intelligence asymmetry translated into negotiating power asymmetry. This perception led the Soviets to insist on more rigorous verification clauses in subsequent treaties, including on-site inspections of missile facilities and restrictions on telemetry encryption. The START I Treaty, signed in 1991, included specific provisions prohibiting intentional encryption of missile telemetry during tests, a belated attempt to level the informational playing field. But these clauses came decades after RHYOLITE had already captured critical information that shaped American nuclear strategy during the 1970s and 1980s. Soviet documents from the Gorbachev era reveal a self-critical reassessment. Internal reports acknowledged that the Soviet Union had systematically underestimated American technological capability in emerging domains, particularly in military applications of space technology. RHYOLITE was not an isolated case. It was part of a broader pattern that included high-resolution photographic reconnaissance satellites, infrared early warning systems, precise satellite navigation for missile guidance, and protected military communications. In each of these domains, the Soviets had assumed that technical limitations would provide inherent protection, only to discover the Americans had overcome those limitations through aggressive innovation and massive investment. The collapse of confidence in strategic communications had direct operational ramifications. Soviet military commanders, aware their transmissions might be compromised, became excessively cautious, reducing communication volume and imposing rigid restrictions even on encrypted traffic. This, in turn, degraded command and control efficiency. Decisions that previously could be coordinated rapidly via microwave links now required physical couriers or cable communications, introducing delays and increasing risk of operational failures during crises. During the 1980s, as the Cold War intensified under the Reagan administration, American capability to continuously monitor the Soviet Union via SIGINT satellites like RHYOLITE and its successors provided American planners with an unprecedented level of strategic knowledge. Every troop movement, every weapons test, every Soviet military exercise was accompanied by a detectable increase in communications that the satellites captured. This enabled real-time threat assessments and calibrated responses, reducing the risk of catastrophic misunderstandings that could escalate to nuclear conflict. The final irony was that by attempting to protect their strategic communications through presumably secure propagation physics, the Soviets created a long-duration vulnerability that the United States exploited silently for over a decade. When the vulnerability was finally revealed, the damage was done. Strategic arms treaties had been negotiated. Weapons modernization programs had been adjusted based on compromised intelligence. And Soviet communications security doctrine had been exposed as fundamentally inadequate for the era of space-based surveillance. Legacy and strategic implications, RHYOLITE established an operational precedent that defines space-based signals intelligence to this day. The capability to position sensitive receivers in geosynchronous orbit, maintaining continuous surveillance over vast geographic areas without risk of shootdown or capture, transformed the nature of strategic intelligence collection. What began as a bold technological experiment in 1970 evolved into a permanent constellation of SIGINT satellites, forming the backbone of American capability to monitor adversaries and allies globally. RHYOLITE's direct successor, the Magnum program initiated in 1985, expanded capabilities with even larger antennas and more sophisticated onboard digital processing. From 1995, the Orion satellites represented the third generation, with expanded constellations of 4 satellites maintaining simultaneous coverage of multiple global regions. Each generation incorporated lessons learned from predecessors: more sensitive receivers, greater bandwidth, capability to process larger signal volumes simultaneously, but the fundamental architecture, geosynchronous orbit and relay via Pine Gap, remained consistent. Pine Gap continues operating today, now housing over 800 American and Australian personnel. The facility has expanded significantly since the 1970s, adding additional radomes, massively parallel computing infrastructure, and high-capacity fiber optic communication links connecting directly to Fort Meade and Langley. Its strategic importance has been repeatedly demonstrated. During the 1991 Gulf War, Pine Gap provided real-time signals intelligence on Iraqi military communications. During post-2001 operations in Afghanistan, the facility monitored insurgent communications and coordinated targets for drone strikes. During regional conflicts in Southeast Asia, the Middle East, and Africa, Pine Gap remained the central node for space SIGINT intelligence processing. RHYOLITE's impact on international relations was profound, though often invisible to the public. The intelligence asymmetry created by American capability to intercept adversary strategic communications without equivalent reciprocity shaped power dynamics during the Cold War. The United States negotiated arms control treaties with detailed technical knowledge of Soviet capabilities, while Moscow operated with significantly more limited information on American arsenals. This informational advantage translated into strategic advantage. After the Soviet Union's collapse, declassified documents revealed the extent of Soviet surprise and demoralization upon discovering that decades of missile telemetry had been captured. Soviet engineers who worked on strategic missile programs during the 1970s reported in later interviews that RHYOLITE's 1977 revelation generated a crisis of confidence. Projects they had worked on for years, believing their activities were secret, were being monitored in real time by American analysts. The effort, the resources, the security measures, all had been futile against a surveillance platform suspended 35,000 kilometers above their heads. RHYOLITE's broader strategic lesson is that technology can transform presumably inherent vulnerabilities into exploitation points. The Soviets trusted microwave propagation physics as a security guarantee. But the Americans weaponized that same physics by positioning receivers where the Soviets imagined it impossible. This dynamic repeats across multiple domains. Submarine cable communications, considered secure, are vulnerable to interception via specialized submersibles, as demonstrated by Operation Ivy Bells. Encrypted communications, presumably inviolable, can be compromised through exploitation of implementation flaws or bulk collection for future decryption when computational capabilities increase. Commercial satellite communications used by governments for unclassified traffic are routinely monitored by intelligence agencies with access to service providers. RHYOLITE also established the importance of rigorous compartmentation and counterintelligence. The program remained secret for 7 years despite involving hundreds of engineers, technicians, and analysts. Christopher Boyce's security breach resulted from personnel screening failures and inadequate supervision, not technical system vulnerabilities. His ability to photograph classified documents and transport them outside the TRW facility without immediate detection revealed procedural weaknesses that were subsequently corrected in later programs through stricter access control measures and security auditing. The international cooperation exemplified by the United States-Australia partnership at Pine Gap became a model for subsequent intelligence alliances. The capability to position intelligence facilities on Allied territory, leveraging geographic advantages while sharing political risks and operational responsibilities, proved durable. Similar facilities were established in other Five Eyes Alliance countries, United Kingdom, Canada, and New Zealand, creating a global intelligence collection network that no country could individually sustain. Finally, RHYOLITE demonstrated that technological superiority, not merely numerical advantage, defines strategic advantage in the modern era. The Soviet Union possessed more ballistic missiles, more tanks, more troops, but the United States possessed superior knowledge of enemy capabilities, enabling more effective strategic planning, more efficient resource allocation, and more advantageous international negotiation. In competition between nuclear superpowers, information was, and continues to be, the ultimate currency of power. When the first RHYOLITE satellite launched from Vandenberg in June 1970, few could predict it would initiate a silent revolution in strategic intelligence. But by listening from space, capturing signals that adversaries believed were protected by Earth's curvature, the United States transformed microwave propagation physics from presumed protection into exploited vulnerability. And when the Soviets finally realized, decades of secrets had already been captured, analyzed, and archived in the vaults of NSA at Fort Meade, Maryland.